In this video, we will learn about vector projections, which can be found in the textbook in section 12.3. Suppose A is a vector from P to Q, and B is a vector from P to R, so that A and B have the same initial point, P. Either A and B point in roughly the same direction, meaning the angle between them is between 0 and pi over 2, or A and B point in roughly opposite directions, meaning the angle between them is between pi over 2 and pi. To define a vector projection, we first consider the case when A and B point in roughly the same direction. If we let S denote the foot of the perpendicular line from R to the line containing PQ, then the vector from P to S is called the vector projection of B onto A and is denoted projection of B onto A. Let's go through that again, this time supposing that A and B point in roughly opposite directions. Let S denote the foot of the perpendicular line from R to the line containing PQ. Then the vector from P to S is the vector projection of B onto A. One way to think of the vector projection is as the shadow of B. Because the vector projection is a vector, to understand it, we must determine its length and direction. Note that if A and B point in roughly the same direction, then the vector projection points in the same direction as A. On the other hand, when A and B point in roughly opposite directions, then the vector projection points in the opposite direction as A. Now, since we understand the direction of this vector, we must now determine its length. The scalar projection of B onto A, also sometimes called the component of B along A, is defined to be the signed magnitude of the vector projection. In other words, the scalar projection of B onto A is the length of the vector projection PS. Let theta denote the angle between A and B. Notice that we have a right triangle with the vector projection PS making up the side adjacent to our angle, and vector B making up the hypotenuse. Therefore, the sine of theta is the length of the adjacent side divided by the length of the hypotenuse, or length of PS divided by the length of B. Solving for PS, we see that the scalar projection of B onto A is the length of B times the cosine of the angle between A and B. Note that we defined the scalar projection to be the signed magnitude of the vector projection. Well, if theta is between 0 and pi over 2, then cosine of theta will be positive, and so the scalar projection will be positive, indicating PS points in the same direction as the vector A. On the other hand, if theta is between pi over 2 and pi, then cosine of theta will be negative, and so the scalar projection will be negative, indicating that PS points in the opposite direction as the vector A. Let's rewrite our formula for the scalar projection so that we can compute it without having to know the angle between A and B. Recall the dot product of A and B can be computed as the length of A times the length of B times the cosine of the angle between them. Substituting in our formula for the scalar projection shows we can write A dot B as the length of A times the scalar projection of B onto A. Let's solve this equation for the scalar projection. Then we can write the scalar projection of B onto A as the dot product of A and B divided by the length of A. Or, regrouping, we have that the scalar projection of B onto A is the dot product of B with the unit vector in the direction of A. Let's summarize what we know about the vector projection of B onto A. We found that it's the vector with length equal to the scalar projection and in the direction of A. To see that this tells us all we need to know, let's take a quick time out for a simple example. If we want a vector of length 2 in the direction of the vector v, we find the unit vector in the direction of v and then multiply by 2. So for the vector projection, we'll find the unit vector in the direction of A and then multiply by the length we want, the scalar projection. Hence, the vector projection of B onto A is the unit vector in the direction of A times the scalar projection, or the dot product of A and B divided by the length of A times the unit vector in the direction of A. As a summary, here are our formulas for the scalar projection of B onto A and the vector projection of B onto A. One more vector you will find useful is the orthogonal projection of B onto A, given by B minus the vector projection. The orthogonal projection is the vector perpendicular to A. This will come up during your web work, but we won't do much with it in class. Let's do an example of computing scalar and vector projections. Let A be the vector 1, 1, 1, and B be the vector 1, negative 1, 1. First, we need to compute the length of A, which is the square root of 1 squared plus 1 squared plus 1 squared, or the square root of 3. Then the scalar projection of B onto A is the dot product of A and B divided by the length of A. So we have 1 times 1 plus 1 times negative 1 plus 1 times 1, or 1 divided by the square root of 3. Finally, we can compute the vector projection of B onto A, which is the scalar projection times the unit vector in the direction of A. So we have 1 divided by the square root of 3 times the vector A, 1, 1, 1, divided by the length of A, square root of 3. Putting this together, we see that the vector projection is the vector 1/3, 1/3, 1/3. That's all for now.